First of all, let me thank ACC and Instruct for giving me this unique opportunity for talking about the topic which is very close to my heart. Okay. Before I getting into any of the discussion, let me have a quick survey. Like now the statement, I'll make one statement that I believe that there is a large skill gap when we talk about design of steel structures in our country. So if you agree with my statement, you can simply raise your hand, right? Yeah. Okay. Thank you. So that's what I'm going to talk about in this my entire talk. I'm going to highlight few, or not all, but of course few of the areas where I have found that there are major gaps into our industry when we talk about our country, specifically in relation to the design of steel structures. Yeah. Okay, if you can just play this video. Now you all must have seen this video n number of times. It was there in the social media before a few years and it created a lot of discussion. If you can play this video, if it's possible. Yeah, but you may be aware about this, that it was a PB structure which was under erection and then it collapsed. There was no wind force, there was not even full loads which were applied, but then also the structure got collapsed, right? Okay. Anyway, let's say this clip is not running, let me start. So let us start talking about IS 800-2007 because this is the most important code for the design of steel structures, right? So if we talk about a quick journey of this code, it was released in 1956 and the latest version we have is 2007. Of course, draft code is released recently. We'll not talk about that. We may talk about that in maybe in the separate discussion. But we can say that we have just only one revision as of now with reference to limit state design. And if we compare in the global industry, the limit state design has been revised more than 5 numbers of times, right? So this is the first revision we can say for the limit state design method for the design of steel structures. So there are a number of questions when we are designing the steel structure. Still today, there are a number of questions. And I can tell you that still IS 800-2007 is not being followed in totality when we are talking about steel structures in our country. And I'll always highlight this area that whatever software we are using, that software must be authenticated. Now, what does it mean by authentication? The software are making claim that X software is in line with certain, let's say, Indian standard code, right? But this is one of the area when I just started my career, and as of today, still I'm focusing on this area. And I'm always passionate about finding out that is there any gap between the software which we are using and the codal provisions what we have. And let me tell you honestly, I have found out so many areas where in which our popular software are somewhere maybe at a higher side or maybe at a lower side. It is not getting aligned with reference to the current Indian standard clauses at number of places. What is the reason? There are a number of reasons for this which may discuss separately if time permits. And I'll highlight a few of those areas as we progress in our discussion. So this is the latest document when what we have for the design of steel structures, right? The 800-2007, now 2 amendments have been issued. Now these 2 amendments what we have right now, these 2 amendments are actually for regularizing NBC 2016. Now what do I mean by that? In fact, whatever amendment number 1 and 2 which we have right now, those were already incorporated in NBC in 2016. And amendment number 2 was only regularization. So that means between the span of 2025 and 2016, we were not following the amendment number 2, right? The majority of the practicing engineers were not knowing this fact. So when we talk about different types of analysis which are mentioned in the 800-2007, you must be, I hope you all must be aware about it. So majority I would say that we are focusing on the first order elastic analysis, but already there are different types of analysis which are already mentioned: second order elastic analysis, plastic analysis, even frame buckling analysis. There is a classification of the sway frame and the non-sway frame, and then it is mentioned in the document that we need to consider horizontal notional loads on the structure. right? But this is what I have experienced while reviewing so many different files from different consultants, that the horizontal notional loads are not considered. Now this is one of the very interesting and one of the very important area when we are talking about imperfection into the steel structures, right? So when we compare to the American standards, they have very clear laws about the horizontal notional loads. We also have, but it is not being become the practice in the industry, we can say, as per my experience. That's what I have said, that the horizontal notional load, those are actually accounting for the imperfection. Now what is written, interestingly, in our Indian code, it is said that the horizontal notional loads need not be combined with the wind and seismic loads. Now, personally speaking, I do not agree with this statement. So when we compare this similar statement with the American standard, it is said that the horizontal notional loads shall be combined with the wind and the seismic load. What is the meaning of it? What is the intent of it? The horizontal notional loads, in fact, we are introducing in the model for accounting the practical imperfections what we have, right? Now those imperfections will be there during the wind and seismic also, right? The buckling analysis is already there in both the software. So if we quickly talk about ETABS and STAD, buckling analysis is there, which can be considered, but generally I have seen that this is not being followed. I'll quickly show how buckling analysis can be considered. So I consider these as a virtual laboratory. So I keep on experimenting on different software. So right now what we see right now, these are the snaps I have taken from the STAD Pro. So sorry, this is from the ETABS actually. So I have taken a portal frame and then I have applied a vertical load. And then I have simulated the buckling mode shifts of the steel structures. Right? And what we see, remember this word, what we see on the screen right now, these all are flexural buckling mode shapes. Okay? Similar buckling analysis I also experimented in the STAD Pro. You can see vertical tower. Purposefully I have made this structure so slender. For example, what number we could see here, 0.13967. So that means the buckling will occur very, very early. For example, if we just go to the previous slide, the factor of 1.575 shows that if I want to create buckling of this frame, then I need to increase the applied load by the factor of 1.575 times, right? That's the meaning of the buckling load factor. So here you can see in this model, you can see this factor is only 0.139. So purposefully I have made this structure so slender so that I can get this factor very small. But again, what is again very important point which I'll make right now, this is considering only flexural buckling. Now what is the meaning of it? As you can see here, what I saying that only flexural buckling is considered in the buckling analysis. Flexural torsional buckling and the local buckling analysis is not considered. And let's talk about two software right now, which is STAD Pro and ETABS. So in both the software, if I consider line element, then flexural torsional buckling and the local buckling is not considered. So for example, if I want to simulate the flexural torsional buckling and the local buckling in the STAD Pro, then the only option what I have is I need to create FEM models. That means I need to create a model using plate elements, right? So I'll just quickly show a couple of models which I just created after a couple of slides. Now, as compared to buckling analysis, Indian Standard Code also said that plastic analysis also can be, let's say, can be considered. But still, I could not see, number of files that still it is not being followed in the practice. Now, this is one of the very interesting area, which is lateral torsional buckling, and the clip which we were just trying to see on the first slide, the structure which failed, and many of the steel structure where failure occur. So one of the very important limit state is the lateral torsional buckling. And what we could see in this slide, as you can see that only vertical load is applied, right? But what we can see here, that this cross section, if we see, so there that cross section is twisted, right? There is a twisting, as well as there is a flexure. Flexure action is will be obviously there. So that's why it is called as a flexural torsional buckling. And now this type of buckling is not considered in StatPro and ETABS by default when we considered it as a member element. So you just remember this point. So one more example, if we apply uniform moment on the simply supported beam, so there will be tendency of this beam, right, to buckle out of its plane, right? That's what we call it as a buckling. It is actually dependent upon so many parameters. Now, why I am going little bit into detail about this limit state? Because this limit state is extremely important when we are actually talking about tonnage of the steel structure. And also it is extremely important when we talk about safety of the steel structure. So this lateral torsional buckling is in fact dependent upon so many parameters, right? Interestingly, it is also dependent upon type of load. So if I change my type of load, based on that, the criticality of this limit state will change. That is very important, very interesting, right? And let's try to see this. Now, what we have in this code right now in the 800 2007, you must have seen this equation. Now, this equation is actually derived for, as we can see in the last part of the slide, it is derived for the simply supported beam having uniform moment across the length of the member. And I consider this as a simplified approach for the lateral torsional buckling. So when I say this as a simplified approach, that means more complex approach or more generalized approach is also available in the code, right? So in our Indian Standard Code, there are two approaches. One is this simplified approach and other approach is generalized approach. So when we talk about StatPro, for example, it is considering this simplified approach, right? That's what I have written here. It is considering simplified approach, right? Now, when we just look at further into the same paragraph, it is very clearly mentioned in the Indian Standard Code that MCR for the different cross sections for the different loading conditions shall be evaluated based on the annexure E of the document. And generally this is what I have seen, that whenever certain part is actually kept as an annexure, then always it is given as a less priority. And that's what has happened with this annexure also. So annexure E is very important. So if we just see the annexure E here, I have just taken few snaps here. In the annexure E, you will see that there is a very long equation which is given for the lateral torsional buckling. And it is having three factors, C1, C2, C3. So what we can see on the screen right now, this factor is C1 factor, which is actually considering variation of the end moment across the length of the member. There is another factor which is C2, which is very critical, very important, and it is actually decrease the load carrying capacity of the member, right? So as we can see from this figure, that if I apply the vertical load at the shear center, then it will not create a twisting. But if I apply similar load on the top flange, or let's say if we take this example, where I apply this load on the top of the rail, right? So then this will create, or rather this will increase the intensity of lateral torsional buckling, right? Now remember, these C1, C2, C3 are not considered in StatPro. We'll come to the ETABS with the examples. I have taken few examples to demonstrate this. And if we just quickly look at to the C1 factor, what is the impact of the C1 factor? As we can see here, the C1 factor is actually coming into the multiplication. So if my C1 factor increases, my moment carrying capacity will increase, right? And if my C1 factor reduces, then my moment carrying capacity will reduce. So what we can see here from this table, if you can see here, the C1 value varies from 1 to almost 2.75, right? Now wherever it is mentioned as a 1, that is the area, or that is the case where we have uniform moment across the length of the member, right? So when I consider xi is equal to 1, where I consider moment gradient equal to, let's say, where m1 is equal to m2, so then it becomes exactly the simplified approach, right, what we have in the document. And for that it becomes 1. But if I have double curvature, just for example, then this value will increase to 2.75, significant increase, right? So this is a extremely important limit state which needs to be considered in the design, right? And there could be, if it is not considered properly, then the error could be on the highly conservative side. At the same time, it could be on the highly unconservative side. And as we have discussed that State Pro as well as ETABS, by default, they are not considering lateral torsional buckling as well as local buckling. Now, this is what I have created this computer model. Now, as you can see, I have modeled I-beam, and I hope you can see the small plate elements. So I have created this entire I-beam using plate elements, right, just to simulate the lateral torsional buckling as we were just discussing. And you can see this. Now, when I apply the vertical load on this member, now this member is buckled. Now you can do this simple exercise. You take this 8 meter of beam, single line member in State Pro and ETABS, and when you apply the vertical load on that transverse beam and you perform buckling analysis, you will not get any results from the software, right? Or rather, your member will not at all fail. But if you will create the same member using FEM in State Pro, just for example, you will be able to see this buckling. So what I mean to say in short, that by default, the line members, whatever we are considering, and even if we are adopting buckling analysis from the software, it is actually not giving us the true behavior which is really required. One more very important thing I have done here. Now I have compared the lateral torsional buckling result from the State Pro and from the ETABS. So right now what we have on the screen, I have taken ISMB 600, which is having, let's say, 8 meter of span. I have purposefully taken longer span of the beam, and I have considered that there is no lateral restraint for the 8 meter. And I have taken UDL of 1 ton per meter, and it is simply supported. So when the analysis is run into the State Pro, just remember this value, which is 32 ton meter. So 32 ton meter is coming as a capacity of the member, right? Now exactly same member, exactly same condition I have considered into the ETABS. And you can focus on this value, which is MD LTB. It is 35 ton meter, right? Not much difference, 30 to 35, not much difference. Now I have changed here with the fixed support plus UDL. Everything is same. I have kept on changing the boundary conditions, the loading conditions, and I wanted to see that whether it is making any impact on the design capacity of the member. Here again it remains constant in the State Pro. When we get to the ETABS, again it is 35, so it's okay for this condition. I have created one more condition, fixed support plus concentrated load, right? We can see the capacity is 32 ton meter. And when we get to the ETABS, now we can see that this capacity has increased from 35 ton meter, now it has increased to 40 ton meter. Why it is getting increased in ETABS? Because ETABS is taking account of C1 factor. It is considering automatic calculation of C1 factor, which State Pro is not doing. So my capacity is increased. Now couple of more exercise I have done here. Now last example is the simply supported beam with the double curvature. Everything is same. I have applied double curvature moment. Again, what we can see that the capacity is remaining same in State Pro. And when we look at to the ETABS, now we can see this capacity is increased from 32 to 65, or we can say from 35 to 65 ton meter, right? What is the reason? Reason is this factor, C1. Now you can see this 2.7 factor. Now it is getting aligned with our annexure E chart, where we are getting the value nearly to 2.75, right? So this is the exercise which I performed before a couple of years, and the software keep on changing. Nowadays software keep on changing at every 6 months, 1 year, right? So we need to perform this kind of exercise just to see, what is the current state. And we must know the limitations and what is actually happening behind the black box, that we must be aware of. So I tried in the State Pro, like, can I simulate, can I consider the 2.7 factor, which let's say in EDAPS it is considered as a 2.7. So I made CMX equal to 2.7. So you can see here, CMS is made 2.7, but it is not having any impact. It is not in their internal algorithm, the value is not getting enhanced. And that's why there are a number of the statements which we received, right, that IS 800 2007 is not economical. But this is one of the reason, right, like and this is actually attributed to the software. And if we go one step further, in IS 800 also, the clause is not written, I would say, the way it can be considered in the software. In the other international standard, for the same consideration, equation is given. In our code, equation is not there. That is also one of the reasons. But still, the software is not calculating automatically. That's a problem. One more area, of course, it is already covered in the discussion, which is the steel connection design. And I strongly believe that steel connection design is one of the greatest gray area when we talk about the design of steel structures. And according to me, still we do not have any single source of, we can say, the means for the software or for the connection design. So when I say means, we have, let's say, manual calculations, software, we have in-house spreadsheets, we have, let's say, RAM connection, we have Idea Statica, or we can have more advanced software like ANSYS. We have multiple options available, but we cannot say that any one solution is perfect solution. We need to use mix of different solutions depending upon the cases and situations. Right? And of course, the pre-qualified connections is not there in the Indian standard. So I am of the opinion that we should have pre-qualified connections in our Indian standards as we have in the other international standards. Of course, let me skip this. Now, importance of connections in the steel structure design, it was already touched upon by Dr. Jaswant. And this is the Northridge earthquake. I also took, I always take that as an example. Right? So it is the same thing, almost same thing. So I'll just keep that part. Yeah. So this is what was discussed. Like there was a failure in the welding, and welding shall be done in such a way that it shall not become weak link. Let's say whenever the earthquake strikes, right? That is the overall concept. And of course, pre-qualified connections must be there according to me. Now, while let's say reviewing number of calculations across the country, this is one more thing which I could see, that the design calculations, or specifically for the connections, are not upgraded in line with 800 2007. So many calculations which came to me were actually in line with the earlier version of the code, which was 1984 version of the code. Now when we look at into 800 2007 section number 10, there are many stringent criteria now introduced. Of course, those criteria are introduced, certain criteria are introduced just only in a small paragraph. I'll highlight a few of those areas also. But the connection design as with reference to 800 2007 is very stringent, I would say, as compared to the 800 1984 code. Okay. Of course, I have taken a couple of more slides with reference to how to decide the type of connections. So let us keep this because we do not have the time. So what I mean to say with reference to this, that the conceptual thinking is important whenever we are talking about the connection design. Of course, now block shear is also introduced in the Indian Standard Code. Right? Now here I have taken this snap from the Euro code just for a discussion purpose, and what we can see on the screen right now, that on the left hand side what we can see, check number 1 to 16. Now what are these check number 1 to 16? They have considered the design of connections which is a component based approach. Now component based approach, that means each and every component of the connection will be designed separately, and of course there is a detailed handbook also available which is giving mathematical equations for different checks, right, which is, let's say, check number 1, 2, 3, 4, etc. So similarly, this is typical one of moment connection, we can say, and for that also we can see that are different checks which are required. Now what is written in our section number 10 of 800 2007, that all local elements and all connection elements to be checked for the applicable limit states, right? But it is not detailed out, and that's why there are all possibilities that certain important limit states will be missed out. So I've taken one of the moment connection right now. This connection I have modeled into the RAM connection software. Now what I've done, I have performed the design of connections in line with the IS 800 2007. I asked the software to perform connection design for IS 800 2007. So it has performed the connection design, but in the output, as we can see on the right hand side, it is everywhere, it is actually referring to the Eurocode, EC3. Yes. What is the reason that there are certain areas, as I said, that which are not very clearly written into our document? Everywhere we can see on the right hand side, EC3 is referred. Okay, there is one more moment connection I have taken. This is from the American standard, we can skip this. But what I just wanted to highlight here, when we talk about any connection, there are so many checks. You can see here from point number 1, 2, 3, these all are different checks which needs to be carried out. So if we are only focusing on the spreadsheet calculations or manual calculations, and if we are not capturing all these different limit states, there are all possibilities that in certain specific conditions our connection may not be perfectly safe, we can say, or may not be suited to the specific project requirements, right? Of course, in the American code, there is a connection which is called as a RBS, where beam is specifically, purposefully, it is reduced at a cross section, at a junction with the column, so that the plastic hinge will actually generate into the beam portion and it will not generate into the column portion. Yeah. One more point, base plate connection, right? If we see the base plate connection, see, when I joined one of the largest MNC in 2005, and at that time, that was one of the major gap area was anchor bolt design. And that anchor bolt design, of course, for the design of steel structure as well as for the design of large vertical equipment, right? And there was so much, I would say, the questions and queries and doubts were there. So we took up one of the assignment, and then we created our own in-house standardized document for the anchor bolt design. And that time, of course, we didn't refer ACI document. Right now, I have taken snaps from AISC document. But what's the important part for the base plate design? That the concrete portion shall not fail first. Anchor bolt should fail first. So that means my concrete should have adequate capacity, right? And that capacity shall be higher than the anchor bolt capacity. And what is highlighted here schematically, that the cones will be generated at the interface of the base plate, at the interface of the anchor bolt, where we have the plate, right? So from that location, this cone will be generated. Now what will happen, interestingly, that this cone portion will be truncated or will be reduced in the size at the edge portion. So that's why, and similarly, there will be overlap of the cone between number of anchor bolts. So that's why spacing of the anchor bolts as well as the edge distance is very crucial. So we developed our in-house thumb rules, our in-house guidelines for the anchor bolts, depending upon the anchor bolt diameter, that what shall be minimum edge distance and what shall be minimum, we can say, distance between the anchor bolt. Of course, one more area, as we can see here, the reinforcement is also very important. Whenever the pull out will occur from the at the anchor bolt location, that is the location where actually hair cracks will be generated in the concrete, because concrete doesn't have any tensile load carrying capacity, right? So this load actually needs to be transferred to the rebar, to the reinforcement. So we need to place this rebar at a closer distance with reference to the anchor bolt, so that this force can be transferred. One more area which will come for the base plate design is the base pressure calculation. So if you refer the RAM connection software, it is using CB-FIP model, right? And as we can see here, what will happen when we consider the pressure calculation, this is the area where the tension is generated. This bolt is actually holding down the structure when structure is trying to lift up at this location, right? And what we can see here in this area, this is the area where compression is generated. So the compression area is relatively larger, we can say, as compared to the location where tension is generated, right? So the lever arm what we will get, that is dependent upon the location where compression force will generate and this tension force will generate, right? And depending upon this lever arm, the balance or we can say the moment will be counterbalanced. Okay, so with this we'll create the pressure. Of course, shear key also we provide in certain cases where shear force or let's say shear carrying capacity of the connection is not adequate. Now here I have just created a couple of examples in the RAM connection. What I have done here, as you can see here, of course here negative sign indicates the compression in the software. So as you can see here, the moment is 35 ton meter, which is the overturning moment we can see at a column location. Now here you can see I have reduced the compression load from the structure, which is only 35 ton. The moment capacity is kept similar. Now what's happening here, of course, what we can see here on the right hand side in the red color is the utilization ratio of this connection, right? So this I was just experimenting and I've just taken few snaps here. Now you just see in the next slide, this ratio has gone to 180 straight away, right? Why it has gone to 180? Because I have clicked this option which is a splitting failure. Now splitting failure, that means whether we need to consider the breakout of concrete or not, right? So if we consider this, then it is becoming so critical in this specific example. So now the further corrections are made, the few trial and errors are made, so to reduce that utilization ratio. So right now, sorry. Okay, so you can see now, okay, what I have done here, embedment length was increased. In the previous case, it was 470 mm. Then here it is increased to 899 mm approximately, right? So with this factor has now come down to 18, from 180 to 18, right? So there will be a lot of trial and errors for this type of connection design. So after performing this design, again we will have a look into this output where we can see, okay, this is the location where 17 is happening. Now it is actually attributed to the combined tension and shear interaction of the connection, right? So accordingly we need to design the connection, we need to upgrade this connection. Now this process we followed for all connections, and we created our in-house standard drawing, so that every time it is not required to design the same connection again and again, so that it will reduce the errors as well as it will increase the efficiency. Okay, this is again a few more trials were done on the same connection. Yeah, okay, and then one more area for calculation of base plate thickness, this Ross formula which we are using. Now when we look at into the RAM connection, it is not having the proper option according to me for the stiffener arrangement what we are doing in the routine practice. So for that we are actually referring to the Ross formula, and based on that stress and strain we are calculating. Okay. Now we already touched upon this 18168 2023, right, in the previous session. So I'll just quickly highlight only a couple of points here before we close our talk. One of the very important point which I just want to highlight, that now it is said that in all seismic zone 5, the steel building shall be made of EBF system, eccentric braced frame systems. SCBF, which is specially concentrically braced frames, shall not be used, and in seismic zone 4 and 5, SMRFs may be used only up to height of 15 meter. In short, EBF is made compulsory, right, in the specific seismic region. That is one of the takeaway from this slide. Of course, we talked about this uncertainty ratio in the previous session. One more important point, if you refer to 18168 2023, there is a section classification is given, and this section classification is in fact more stringent as compared to section classification what we have in 800 2007. more stringent in the sense our thickness of the flange or size of the section will actually increase. Okay, one more clause which is written, and of course I am failed to understand this, that it is mentioned that columns in buildings designed to resist lateral loads shall not carry tensile forces, right? But it is going to be there according to me. I think few more clarification is required for this. Of course, for the strong column weak beam, this factor is now 1.4. Okay, we also talked about this 0.04 radians, and this is a snap of the eccentric braced frame. Okay, there is a 00 time is up. Okay, so I have conducted a number of online courses, online sessions on the steel structures, and we are still planning a number of sessions on the steel structures with this. Of course, this is the our YouTube link. I think many of you might be having this link, but this is the place where so many free resources are available. So you can just log into this and you can watch this. Right? Okay. So with this, I conclude my talk for the design of steel structures. Thank you.